Alright, what's up guys? In this video I'm going to pick up some calculus here, and this is going to be another integration practice video, and this is going to be example number 26 of the integration practice series. Alright, so we're asked to deal with the integral of 5x minus 7 over x squared minus 3x plus 2. Okay, so this is a good time to use partial fractions. So keep in mind, for partial fractions, to use this method, you need to be dealing with a proper fraction, where I have p of x over q of x, where p of x has a degree that's less than that of the denominator. That condition needs to be met if you want to use partial fractions. If it's not met, you can't use the method, or you can do in some cases some polynomial long division to reduce the degree of the numerator to get it to a point where you can actually apply partial fractions. But that's very important to remember. Also, it's important to remember that you don't need partial fractions all the time. There may be some integrals that look somewhat similar to this that you can easily complete the square. I think an integral that I posted the other day looks somewhat similar to this one, that you would have thought, okay, partial fractions, but we completed the square and did it with a u substitution after completing the square. So partial fractions isn't needed all the time, but it is helpful for situations like this. So what you have to do for partial fractions in this particular case, we need to factor the denominator here. So we have x squared minus 3x plus 2. We need to factor that. Also, make sure you go back and review factoring and stuff like that from algebra. If you're a little rusty on that, that'll become an issue when you get to partial fractions. So go back and review that, but other than that, you'll be good. That's just going to be x minus 1 multiplied by x minus 2. And you can check me on that by just foiling it, but that's what it's going to be. So now we take this integral here, and we got 5x minus 7. And all I did here was to kind of factor my my denominator here. And so now we have a over the first term, which is x minus 1, plus b over my second term, which is x minus 2. Actually, the best way to write it, I'm going to take the integral sign off. So the best way to write it is this way. Because you'll see the next step that we do here will be more clear without that integral sign being there. Okay, so that's actually the better way to write it. Okay, so remember what we do with partial fractions. And by the way, if you're still rusty on partial fractions, I got plenty of videos on it, so this is the only example to look at. So what we're going to do is we're going to take this denominator over here, which is x minus 1 times x minus 2, and multiply it by both sides. So we'll multiply it on this side, multiply it on that side. So I'm just going to put it over here so that you can kind of see what exactly is happening. Now, partial fractions, the method or the technique is one of those techniques that you really don't see the whole point of it until you kind of get through most of it. So you may not understand what's going on right now. You're probably like, oh man, this just seems so useless. But you'll see how with this technique, it takes an integral that we can't deal with, because there's no way a u substitution would work for this. Because to do a u substitution, let's just say if we set the denominator as our u, well, the derivative of that would just be 2x minus 3. How does that help us? We would need its derivative to be in the numerator somewhere, which is not. So we know a u substitution won't work. And basically what this method does, or this technique does, is it allows us to take some integrals that we don't know how to deal with and break them down into integrals that we do know how to deal with. So now that we multiply both sides by this denominator over here, that clearly just leaves us with 5x minus 7 over on this side. The x minus 1 canceled out, but I'm still multiplying by x minus 2. So this would be a multiplied by x minus 2. And then we'll have plus b multiplied by x minus 1, because the x minus 2 canceled out. And this is where we arrive at. All right, so the way you go about finding the value of these constants is going to vary depending on the problem. So the first way of doing it is the way that everybody likes to do it, is to simply substitute some values of x in and try to solve for the constants. That works a good majority of the time, but it doesn't work all the time. And then the second way is the way that most students don't like, is equating coefficients and solving the system. In this particular case, we could easily just plug in values of x and solve for the unknowns or solve for the constants, but don't expect it to always be like that. It won't always be that easy. So we just need to pick some values of x that we can substitute in that allow us to solve for, let's say we want to solve for a first. Doesn't really make a difference which one you solve for first, but let's just say you want to solve for a first in this particular case. Well, notice that if we let x equal positive 1, well, if I substitute a 1 in for x, I'll get 1 minus 1, which is 0. If I multiply b by 0, remember b is just a constant. We don't know what it is, but it's just a constant. It's just a number is what it essentially it's going to be. So if I multiply any constant times 0, even though we don't know what it is yet, we get 0. And so what that's going to do is it's going to cancel out b and it's going to isolate a. So let's let, or it's going to leave a behind. So let's substitute in 1 for x. Now you have to make sure you plug it in everywhere. So it's very important that you do that. So in this case, we get, and you'll see why this works here in just a moment as we continue. So as you can see here, the beat goes, and over here we continue with the whole process. So here we'll get -2. And it looks like we'll get -a. Now we need to solve for a. We don't need -a. We need a. So therefore, we can say that a is equal to +2. So we can divide both sides by -1. And that gives us the value of our first constant. So this is the easiest way to do it, but it doesn't work all the time. All right, let's try to find b now. So to find b, it's pretty much the same procedure. We need to pick an x value. So obviously we can let x equal 2 and plug that in there. So we'll get 5, 2, -7. In this particular case, we don't have negative numbers, but if you end up getting a problem where you have negative numbers, make sure that you're putting parentheses around those, because it's very easy to make a mistake if you don't put parentheses around your negative numbers. So very similar to what happened up here at the top, a canceled out, and we could just solve for b now, and that's pretty easy to do. So let me get another sheet. So this is what we had after substituting in a2. We would just end up getting 3 is equal to b, or we could say that b is equal to +3. That would be the value of b in that case. So what was the whole point of this whole thing? Well, if we go back to the integral that we were originally dealing with at the beginning, which was the integral 5x minus 7 all over x squared minus 3x plus 2. We basically took this integral that we don't know how to do and turned it into one that we now do know how to do. So if you go back to what we did up here at the top, and you notice that we had the values of our constants, we didn't know what they were. We now have found those, so all we have to do is plug them in. So let's do that. So now this integral that we couldn't deal with effectively becomes the integral 2 over x minus 1 plus 3 over x minus 2 integrated with respect to x. Now, doesn't this look like an integral you know how to work with better? Of course. Now, one thing you need to keep in mind with these partial fractions when you're using this technique, a lot of these partial fractions integrals yield to your natural logarithm integrals. I don't want to say all of them because that's not true, but the vast majority of them do. So make sure that you can easily integrate things like 1 over x or 2 over x minus 1, or 3 over x minus 4, or 7 over x plus 9, or something like that. Make sure you can do those because most of these partial fractions will yield to these natural logarithms. Now, we know, and I can actually just go ahead and write the final answer and kind of kill two birds with one stone. So I'm going to write the final answer. So the integral we were asked to deal with was 5x minus 7 all over x squared minus 3x plus 2. And so basically the answer that we're going to get, let's go ahead and integrate. So remember the antiderivative of 2 over x minus 1, that's just going to be 2 ln absolute value of x minus 1. Similarly, we'll integrate 3 over x minus 2, and again, that's just 3 ln absolute value of x minus 2. And this is an indefinite integral, so what do we need? We need the plus c at the end, and that will be our solution. And that's how you evaluate this integral using partial fractions. Alright, so this one was a relatively easy example, and this is an example I recommend someone looking at for if they're seeing it for their first time. However, as with anything in math, it won't always be that easy. And I do have some partial fraction integrals that I have done on video that are far more difficult, that require a little bit more work. So don't expect them to all be this easy. So if you want to see ones that are a little bit more challenging, I do got videos on those. But this is just a good one for a beginner that maybe just needs to see how the method, how the technique actually works. So that's going to be your answer. So let me know if you have any questions, and I'll see you next time.